Alright, in example 2, we're going to determine the expected payback for a game of chance. So suppose a game requires you to choose 4 cards from a standard deck, 1 heart, 1 spade, 1 diamond, and 1 club in that order, from the 13 cards in each suit. There is a single winning combination, and if you draw the winning combination, you get $5,000. It costs $1 to play. Find the expected payback for this game. So there are 2 possible outcomes for our random variable x. We can either win or we might lose. So we need to assign a value for each possible outcome here. Well, if we win, we would win $4,999 since it costs $1 to play the game. And if we lose, well, we lose $1. So we'll assign that a value of -1. So now we need to find the probability of each outcome occurring. Alright, so let's see. So let's first compute the probability of winning. So we've got 4 cards to choose, and we're choosing a card from each suit. So let's see, hearts, and then we've got the spades, diamond, and the clubs. Okay. Alright, so in each suit there are 13 cards, so the probability of choosing the winning heart would be 1 divided by 13. And similarly, the probability of choosing the winning spade would be 1 out of 13, and same for choosing the other winning cards. Now, to find the probability of winning, we would just multiply all of these probabilities together because of the multiplication rule. All of these events are independent. Choosing a card from one suit isn't going to affect your choice from any of the other suits. So then, the probability of winning would be 1/13 times the 13th times the 13th times the 13th, or just 1 divided by 13 to the 4th. Now let's compute the probability of losing. So, well, the simplest way to compute this probability is to remember the fact that the probabilities in a probability distribution sum to 1. So then, then the probability of losing would have to be 1 minus the probability of winning. So 1 minus 1 divided by 13 to the 4th. So now we have our probabilities. We can compute the expected payback. So then E of x is equal to 4,999 times the probability of winning, so 1/13 to the 4th, minus 1 times the probability of losing, so 1 minus 1 divided by 13 to the 4th. And rounding to the nearest hundredth, this is approximately -0.82. So notice, like the first example, it's impossible to actually lose exactly 82 cents in any given game, but on average, you'll lose 82 cents per game. So in this case, we would call this an unfavorable game.